Hello and welcome to this lecture. So, we've been studying about orthonormality, orthonormal basis, in general orthogonality and all that. We're going to put it to some use right now in this lecture and talk about least square solutions and a minimization problem which has far reaching applications in so many areas across all engineering disciplines and all that. Okay, that's this least square solutions idea. Let me talk about it next. Okay, so here is the motivation. So, we've seen that linear equations have a huge number of applications. Everywhere you see there are linear equations that you have to solve, and quite often what will happen is you will end up in a situation where you have Ax equals b as your linear equation. A, let's say, is an m cross n matrix, x1 to xn is the variables and b1 to bm is the constants on the other side. Now, if you look at how solutions exist and don't exist for such a system, you have Fm, which is your space of all possible vectors with m coordinates, right? That's this big egg-shaped picture. And inside that, there is a smaller space, which is the column space of A. Okay, generally smaller space, maybe it's the whole thing, depends. Okay, column space of A, the space spanned by the columns of A. Okay, now the main point is this: if this B vector, the vector B, lies inside the column space of A. Okay, right? See, remember the column space is an m coordinate space, right? So A1 to AM1, so it's inside Fm, just to confirm. Okay, now B also is m coordinate. So if B ends up inside the column space of A, okay, then there is a solution possible here, right? See, this spans the entire space. A linear combination will give everything inside column space, and this B is inside that, so you will get a solution, no problem. Great. Quite often it will happen, you will come up with a linear model, and then this B that you want to solve for doesn't quite live inside your linear model, right? So, as in B is outside of this column space. Now, this may happen for a wide variety of reasons. Your real system may not actually be linear, right? May not be this kind of constraint, but you're approximating, right? So, quite often your models approximate. So, you want to be able to deal with a situation like this. When this B is actually not in the column space, okay, what do I do, right? My system has no solution. Can I not proceed with anything? I'll be stuck if I can't solve this equation, right? Maybe the solution to this equation is an input to some other system design, right? So I need to really solve it, but then this equation by itself has no solution, right? So how do we tackle this problem, right? So when there's no solution, what do? We can try to approximate. Now, anyway, your models, all models are approximations in reality. So maybe the solution you can approximate, right? So how do you approximate? I have shown some blue thing here as maybe something that is close to B. Okay, so can we find an x for which Ax maybe is not equal to B, but it is close to B. Okay, so this B is outside. No Ax will ever be equal to B, but can we find an x such that this Ax is sort of very close to B, the closest among all the possibilities, right? Do such things exist? How do we define them? How do we make sense of them? That's where this notion of least squares and all of that comes in. So the entire idea hinges on this closest vector in a subspace kind of notion. Okay, so what do I mean by that? So here is Fn now, I'm taking a general space Fn, and then there is a subspace of this, which maybe I called S here. I've generalized from the previous case, right? So previously I had column space, which anyway is a subspace. So I'm going to look at a general subspace S inside an vector space Fn, and there is a vector V which is outside of this subspace. Okay, and the question I ask is, what vector in S is closest to V? Okay, so this is very similar to my previous approximation problem in the linear system of equations, isn't it? What vector in this subspace S is the closest to V? Now, if V itself is inside S, the answer is immediate, right? The answer is V itself, right? So it's very easy to solve this problem. But the interesting case is when V is not in S, okay, and you still want to solve this, and you still want to find a good approximation for V inside of S. Okay, can we find this vector which is closest to V, right? So it turns out orthogonality, orthonormality, all of these things play a very important role in this. It may not be very apparent to you now, but there is a crucial point which will help us later. Okay, first is we need a notion of how to define close, right? So for this, our notion of norm and our notion of distance that we defined using inner product will come to our help here, right? So if you have two vectors u and u2, the distance between these two vectors is absolute value. I mean, not absolute value, the norm of u1 minus u2. So let me just talk about this just a little bit, just to be sure we understand. So let's say u1 is a vector which is a1 to an, and u2 is a vector which is b1 to bn. I'm going to think of the distance between u1 and u2 as u1 minus u2. What is this? This is square square root of a1 minus b1 whole square plus so on till an minus bn whole square, right. So, another way to do this is, if you do not like the square root, you can get rid of the square root and you just get this. Okay. So, this is called Euclidean distance, this is called squared distance, right, squared distance, right. You are squaring the coordinates and adding them up. So, it is a squared distance. So, this notion of square enters intrinsically into this notion of norm that we have. So, this norm u1 minus u2 we will think of as a distance, and we saw a lot of examples before to justify why this norm plays the role of a distance, right. So, we know that. So, what question do we ask now? Out of all the w that are in S, okay, there are very many vectors in a subspace S. Out of all these w, find a vector for which norm w minus v is minimized, the lowest possible w minus v that you get. You try all possible w, find that w which gives you the lowest possible w minus v. We saw this problem earlier in the R2 case also, right, distance from a line. I will remind you of it soon enough. But here is notation. This notation is important to understand. This problem out of all w in S, finding a vector for which norm w minus v is minimized is succinctly written in this notation: min over w in S, norm w minus v. Okay, so this is my what's called the objective function, and I'm minimizing it over the variable that I have, which is in fact a vector here, right. So, minimize over all vectors and says norm w minus v. Okay, so what is the answer you will get out of this? There will be two outputs, right, for this problem, minimization problem. There are two answers you will get. One answer is what I call W star. Okay, W star is what is the argument of this minimization, as in that W which achieves the minimum here. Okay, so that is W star. So, this W star will actually be in S, isn't it? So, this W star will belong to S. That is an important thing to remember. Okay, it is a vector in S and that achieves this minimum. Okay, so this W star is the vector that achieves the minimum. And the other output you may be interested in, d of v comma s, it's sort of like a secondary output in some sense, is the actual distance itself, the actual closest distance, the w star minus v. This is the least possible distance that you can have. Both are interesting, but w star is much more interesting to us. Okay. So, this is the problem of finding a closest vector in a subspace. It's not clear whether this problem can be solved easily, right. You may have a 50-dimensional subspace of a 100-dimension space, it's a huge dimension, you have a long vector here and somebody has defined those bases. How do you go about doing this problem, right? So, it's not clear whether such problems have solutions. We will see that there is a very easy solution if you use ideas of orthonormality, orthonormal basis and all. Okay. So, let us see a version of this problem in R2. We have fully solved this problem in R2, which is distance of a point from a line. This is what we saw before. The subspace, my ambient space is R2, and the subspace S I have is the span of just one u, right. So, the span of u is basically the the straight line through the origin and u, right. So, we know this, and we have a point v which is outside of this line, and we want to find this w star which is closest to v on this line as per this usual squared distance, right. And we have this w star, all these definitions. So, here what you can do is you can do this u cap, which is u by norm u, and then the solution for w star ends up being some sort of a part of v that lies along u, which we have seen before in the orthogonal decomposition also, inner product v comma u cap times u cap, right. So, you project v onto the line. That is what you do here, right. So, you take the inner product with v and u cap and then multiply it with u cap. So, the part of v that lies along u. Okay. So, that is w star. Okay. Here is a very interesting property that we saw here. It turns out for that w star which achieves this minimum, which is closest to v, the line from v to w star is perpendicular to the line. Okay. So, it's sort of easy geometrically for you to visualize, but this is expressed in vector spaces by this relationship. V minus w star is perpendicular to u cap, as in the inner product, right, of v minus w star comma u cap or comma u ends up being equal to 0. So, perpendicular from v to line gives you the minimum point. So, we solved this in good detail here. It turns out a very similar formula and method extends to arbitrary dimensions, and that is because of orthonormal basis. And let me show you the answer first. We will prove it later, but for now we will see the answer. Okay, what is the answer in arbitrary dimension? I have an Fn arbitrary dimension space. I have a subspace S of arbitrary dimension. It is spanned by k vectors u1 to uk, but here let's say the u1 to uk are an orthonormal basis. That is important. Okay, so I know any subspace, every subspace has an orthonormal basis. So this subspace is of dimension k, isn't it? It has got an orthonormal basis u1 to uk, which means dimension is k, and I have a k dimensional subspace in an n dimensional overall vector space, and I'm asking for this problem out of all w in the subspaces, which is closest to a vector v, and I have my answer as w star, and I'm going to use an orthonormal basis to specify s. Once I have an orthonormal basis, it turns out this w star as an explicit formula. Okay, it might be surprising to you, but there is an explicit formula which is basically nothing but projecting v onto s. Okay, so previously in one dimension we saw you projected v onto the line. Now you project v onto s. How do you do it? You take v, take a dot product with u1, the first vector in an orthonormal basis. Remember, u1 to uk is an orthonormal basis, so norm of u1 is 1. Previously I was doing something else. Here norm of u1 is 1. Keep that in mind. So I take inner product v comma u1, multiply with u1. Okay, but remember, s is now k dimensions. I can't just stop here. I have to do it for every other vector here. So plus v comma u2 inner product multiplying u2 plus so on till v comma uk, the inner product multiplying uk, and this sum turns out to be the answer w star. So w star is precisely given by this expression. Okay, so it's an explicit, clear answer using orthonormal basis. Without orthonormal basis, you won't get this easy an answer. Okay, now there is another interesting property here. So it turns out once you define w star like this, v minus w star, that vector ends up being orthogonal to every ui. Okay, so previously also we had the orthogonality property in one dimension, two dimension in R2. That same orthogonality property carries over to arbitrary dimensions. So v minus w star, the vector that you started with minus its approximation. Remember, w star is in S, right? Keep that in mind. W star is in S. So this v minus w star ends up being orthogonal to every ui in the basis. That you can quite easily show. And then because of that, here is the interesting property. Now if it's orthogonal to every ui, it's orthogonal to everything, right? So this v minus w star is orthogonal to the entire subspace. Okay, so there is this vector which is orthogonal to the entire subspace that but passes through v, and where it hits the subspace, that w star ends up being the closest vector to v. Okay, so look at the similarity between straight line and the orthogonal, etc. Same idea carries over because of this orthonormal basis property. Okay, so we're going to prove this, but remember this fact. These facts are very, very important. The closest point is simply given by this orthogonal projection, and that is a very simple formula. And there is an orthogonality that is maintained between v minus w star and every vector in the subspace you are projecting to. Okay, so how do you prove this? So we'll prove. Okay, in fact, here is another very interesting point. This w star is unique. Okay, so this I gave you an explicit expression, so clearly it's unique, and it turns out that's another property. We'll prove this in a more abstract way later on. Okay, so let's see proof of this. We'll prove these two properties, this orthogonality and this solution. We'll prove these two. Will prove this uniqueness. Will prove later. Okay, so how do you prove that? First, you have to prove the orthogonality. Let's start with w star. Okay, so this I'm claiming is my solution to that problem. So I have to claim, I have to prove the orthogonality, right? How do you prove the orthogonality? Let's start with v minus w star. What is v minus w star? This expression, right? V minus this inner product u1 minus inner product uk. And it's very easy to see. You remember the Gram-Schmidt side type method that's coming here. So this is also the same thing. You can show very easily that if you do v minus w star comma ui, the inner product on both sides here with ui, sorry. So this equation, I'm taking inner products on both sides with ui. What will happen? The first term will do inner product, you will get v comma ui. This term, when it does an inner product, you will get 0, right? Because you are doing an inner product with u1 comma ui, and if 1 is not equal to I, that will go off to 0, because the u1 to uk are orthonormal basis for S, right? So the only term that will survive is the v comma ui term, right? So there is a v comma ui term that alone will survive, but that will have a v comma ui multiplying ui comma ui. What is ui comma ui? 1. So this v comma ui minus v comma ui will cancel and you will get a 0. Okay. So it's very trivial to show that this w star defined in this fashion, v minus w star is going to be orthogonal to every ui. This was the basis of the Gram-Schmidt process also. We've seen this before. So this is orthogonal to every ui, which means v minus w star are orthogonal to all vectors in S. It turns out this orthogonality is the important property. Once you have the orthogonality, the minimization can be very easily shown. See, remember, we claim that this W star solves the minimization problem, right? So, we are going to show that now because using this orthogonality. If you take any u in S, okay, you can find the distance between V and U, right? What is that distance? Norm V minus U squared. Now, this distance, I am going to introduce my W star inside artificially. Okay, notice how I am doing this. I am subtracting a W star and adding that back again. Okay, so instead of just looking at V minus U, I am looking at V minus W star plus W star minus U. Okay, is that okay? Nothing has changed here, it's the same thing. But now I have my V minus W star and I can hopefully compare V minus U with V minus W star. Okay, so it's a useful little trick. It's used in many proofs. It's a very useful trick. Now let's look at each of these terms, right? What is this term? W star minus U. It is something, but it is something that belongs to S. Okay, that is the key. U is in S, W star is in S, right? W star is also in S. So W star minus U belongs to S. So this vector, whatever it is, belongs to S. Now what is V minus W star? V minus W star is orthogonal to everything in S. So this V minus W star and W star minus U are orthogonal, are perpendicular. Now that's the crucial property. Just by adding this and invoking this orthogonality property, we'll be done. You'll see. So now when we have two vectors orthogonal adding and you're doing norm square, you can use Pythagoras. What does Pythagoras tell you? It's equal to norm V minus W star square plus this norm W square, plus of course some dot product will come, but the dot product will go to 0 because these two are orthogonal, right? So that is Pythagoras theorem, isn't it? So you have norm V minus W square plus something, and this something is positive, right? Non-negative, it cannot be negative, which means for any u in S, norm of u V minus U squared is greater than or equal to norm of V minus W star square. How wonderful is that, right? So if you manage to find a W star such that V minus W star is orthogonal to all in S, you are done. That W star will be the closest to V. Okay, any other u, V minus U square will be greater than or equal to V minus W star square. Okay, so that's it. That's the proof. It's straightforward, easy proof, a few lines, but you get a very clean, full formula, complete formula for the closest point in a subspace to a point outside. Okay, the uniqueness we'll prove later. It's sort of like an artificial. In the way I gave you the answer, it seems unique, but it's good to prove it. We'll prove it later. Okay, so how do you use the closest vector in subspace to solve the linear equation? See, that's what we wanted to do, no? So I'm going to use that here. Okay, use those orthogonality properties and all of that, that projection set sort of idea, and solve this linear equation. What is this called? This is called least square solution to a linear equation. Okay, so it's most useful when B is not in the column space, but even if it's in the column space, you can use, you'll get the same answer, right? So we've seen that before. So here is my linear equation, and here is what I'm interested in. I have to find over all x, that x which minimizes B minus Ax, right? So that's what I want to do. And this Ax is a representative from the column space of A, so it's exactly like a subspace problem. Now what does my orthogonality tell me? My orthogonality tells me the optimum x star will satisfy this property, right? B minus Ax star. So Ax star is my W star, right? B minus Ax star is going to be perpendicular to the entire column space of A. Every vector in the column space of A, B minus Ax star is perpendicular to. Okay. So what does that mean? Column space of A is nothing but the span of the columns, right? The first column I may call W1, the last column I may call Wn, right? So first column, second column, so on till last column. Column space of A is the span of these guys. Of course, I can create some bases, etc. from it, but let's just keep it a span of everything, right? Now, since B minus Ax star is perpendicular to the entire column space, it's going to be perpendicular to every Wi, isn't it? I equals 1 to n. That's the same as the inner product B minus Ax star comma Wi being equal to 0 for every I. Okay, so far I have not said anything new, but except that what this x star, whatever it may be, B minus Ax star has to have a dot product with every column going to 0. Okay. So just remember, this is the inner product and you may have to conjugate if it's complex, that alone you have to remember, but other than that, this is just a straightforward property of inner product going to 0. So this B minus Ax star has to satisfy this property. Now it turns out this inner product, we have seen this before also, can be written in terms of matrices. How do you write that? So if you do u comma v, generally two vectors u v, we tend to write u and v as column vectors, right? U is u1 to u and v is v1 to vn. Okay. You can define this v Hermitian, which is actually a row vector, with V1 bar to Vn bar, conjugate of V1 to Vn, and then you see that the inner product u comma v, which is u1 v1 bar plus so on till un vn bar, can be written actually as a matrix product. How do you write this? This is nothing but v Hermitian multiplied by the matrix u. So, this v Hermitian is a row matrix, u is a column matrix. When you multiply a row matrix with a column matrix, you get a scalar, which is this guy, and that's the inner product. Okay, so hopefully you see that these are exactly identical. Okay. So, a quick word, I just want to repeat it. So, the distance between u and v is this square, so that is where this name least squares come from, least square solution, because I am dealing with a squared error distance here. So, this distance squared is actually a squared error like this. You subtract the coordinates and square them and add them. So, that's why it is called least squares. Okay. So, how do we put this kind of a matrix thing into use? So, we can rewrite this inner product condition in terms of matrices. How do I do it? So, yeah, this is called square distance. Okay. So, let us move this orthogonality to the side, and then notice that this inner product equal to 0, b minus ax star comma wi equal to 0, it is the same as wi Hermitian times b minus ax star equals 0. Okay, that is the same condition we saw, right. So, if you go back to the previous one, you see that the inner product uv is v Hermitian u. That is all I am using here. Okay, so, this inner product I am writing as wi Hermitian times b minus ax star equal to 0. This I can multiply throughout and get wi a x star equals wi times b. Of course, Hermitian is there. Wi Hermitian a x star is wi Hermitian b. So, what is wi? Again, remember, it is the ith column, right. So, this ith column is wi. Wi Hermitian is the row vector with the conjugated entries from the ith column. Okay. So, this is the equation I am getting. So, the last line here is this Wn Hermitian, which is the row a1n bar all the way to amn bar, that multiplying ax star is the same row multiplying b. Okay. So, what I have done here is I have put down all these equations together, one below the other, and I have written it in matrix form. Okay. Instead of writing individually, I have written it in matrix form. Remember, ax star is just a column vector, right, and b is also a column vector. So, all these multiplications are very reasonably valid. Okay. Now, this matrix here, this special matrix here that you see here is very similar to A, except that I have done some Hermitian type operation. I have conjugated and I have made the columns into rows. Okay. So, it is sort of like transpose conjugate, right, conjugate transpose as they call it, that has the special name A Hermitian. Okay. Notice how this conjugate Hermitian and all is appearing naturally in a least squares problem, A Hermitian. So, this if I call this as A Hermitian, this entire equation actually becomes A Hermitian A x star equals A Hermitian B. Okay. So, this is called if instead of solving Ax equals B, you solve A Hermitian A x star equals A Hermitian B, you are doing a least square solution to a linear equation. Now, of course, if B were to belong to the column space of A, this equation and this equation will give you the same answer. If B were not to belong to the column space of A, this equation Ax equals B has no answer. On the other hand, this equation will have an answer. A Hermitian A x star equals A Hermitian B will always have an answer. We saw that, right? That is the least square solution. So, you project the V, the unknown vector B, right, in this case B, onto the column space of A, you will get a valid answer. So, this equation you may be surprised to see, but A Hermitian A x star equals A Hermitian B has a unique solution all the time. So, you can always find the unique solution. So, that is what is nice about least square solutions, right. So, least square solution, once again, if you write up a linear equation, you see that the linear equation has no solution, you can always go back to the least square solution. It will not give you the exact answer, but it will give you something approximate. Okay. So, here are a couple of examples. I will urge you to try it. Just a quick comment on what these things are. So, you can see here, this is 1, 2, 2, 4, right. This is 2 times the first row. So, every second entry has to be 2 times the first entry in the column space, but here you have 1, 1. Okay. So, 1, 1 clearly does not belong. So, you can do a least square solution. You can do 1, 2, 2, 4 multiplying 1, 2, 2, 4 again. Okay. A Hermitian is equal to A in this case. You do that, you will get an answer. The second one maybe I will do again. This has got a very simple form here. So, let me try this. Okay. So, the problem is to solve in least squares. A is this. So, A Hermitian is now there is no complex entries here. So, that way it is nice. So, by the way, B became 1, 1, 1, right. So, the equation I have is A Hermitian A. So, A Hermitian A equals maybe I'll write it down just to make the multiplication easier. 1 1 0 0 1 0. This will actually be 2 1 1 1. Okay, so this is my matrix, and I also need A Hermitian B, right? A Hermitian B. This is 1 1 0 0 1 0 multiplying 1 1 1. You get 2 1. Okay, so you see here once again, by some magic, your x1 star x2 star has to be equal to 2 1, and clear enough, you got a unique solution that x1 x star, I'll write x star is equal to 1 0, right? So you can just by inspection see that the first column has to come here, so you get 1 0 as the answer. So the closest vector to this 1 1 1 in the column space here is just 1 1 0. So closest vector to this guy is just 1 1 0. So this is the closest vector in squared error distance. Okay, so that concludes the lecture. I hope you got the idea of least square solution to linear equations. Thank you.